Determine the inverse Laplace of the expression 2s squared plus 10s over s squared minus 2s plus 5 over s plus 1. Now, we want to write the denominator as a product of factors, and preferably every factor is of the form s plus or minus a constant. So here we have s squared minus 2s plus 5. And the first thing that we should try is to see, can we factor this any further? And the answer is no. So what we'll have to do for that first part is we'll need to complete the square. So complete the square. And then we're going to use that the general partial fraction decomposition looks like s minus alpha squared plus beta squared in the denominator. So that's what we want to make this look like. And then the numerator will be a constant times s minus alpha plus a constant times beta. So when you complete the square, we take half of negative 2. So half of that gives us negative 1. Then we have s minus 1 squared. And then we have to subtract from that negative 1 squared because we introduced that extra term here. And then we add 5 to it. And it turns out that it's s minus 1 squared plus 4. And so that gives us plus 2 squared. Now, if the term is not a perfect square, so if you would end up with s minus 1 squared plus 5, you would just write that as square root of 5 squared. In this case, it is a perfect square, so that's good because that will make our work a little bit easier. So we replace that in our expression here. So when we take the inverse Laplace, we're going to take the inverse Laplace of 2s squared plus 10s. And then we're dividing that by s minus 1 squared plus 2 squared. All of that multiplied by s plus 1. And we know we can break that down into the inverse Laplace of, and now we're going to break down that blue part. Our denominator is going to be s minus 1 squared plus 2 squared. And then in the numerator, we're going to have a constant, which we'll just call a times s minus 1. And then plus a constant times beta. So that is going to be plus beta times 2. So our beta is 2, and I've called that constant b1. I just called that b. And then we're going to add to that s plus 1 in the denominator. And then there's just a constant in the numerator, and we'll call that constant c. So we can, at this point, figure out what A, B, and C are, and then break it down later. But we might as well go ahead and break this down. So this would be the Laplace inverse. So due to linearity, this will be A times the Laplace inverse of s minus 1 over s minus 1 squared plus 2 squared. And now I'm breaking this fraction up, so I can then write this as plus b times the Laplace inverse of 2 over s minus 1 squared plus 2 squared. And then finally, I have plus c times the Laplace inverse of one over s plus 1. And now what you should do is you should look up in a table of Laplace transforms what this expression relates to in terms of the original function t. And hopefully you see that you can compare that with s minus a over s minus a squared plus b squared. And that is the Laplace transform of e to the power at cosine of bt. And so that first Laplace transform, we see that a is 1 and b is 2. So our Laplace transform there, or inverse Laplace, becomes a times, and then e to the power 1t, so that's e to the power t cosine 2t, and then plus b times, and now what we have to compare this with is b over s minus a squared plus b squared, and that is the Laplace transform of e to the power at sine bt. And so again, b is 2, a is 1, so this is plus b times e to the power t sine 2t. And then finally, we compare that expression right there with 1 over s minus a, and that is the Laplace transform of e to the power at c times e to the power negative t. All that is left to do right now is to find the values of a, b, and c. And we do that by looking at the original problem. We had 2s squared plus 10s, and then that was divided by s minus 1 squared plus 2 squared times s plus 1. And we set that equal to the decomposed fraction. So that is a times s minus 1 plus b times 2 all over s minus 1 squared plus 2 squared. And then the second part of our decomposed fraction is plus c over s plus 1. And then what we do to simplify this is we multiply both sides times the denominator on the left. So we're multiplying by s minus 1 squared plus 2 squared, and then times s plus 1. And when we do that, on the left, this cancels out, and we're left with 2s squared plus 10s. And that equals, here for the first term, the s minus 1 squared plus 2 squared cancels. So we have a times s minus 1 plus, oh, and this should be b times, no, that's b squared. That's b. Sorry. That's right. So plus 2b. The square only shows up in the denominator, not in the numerator. And so we multiply that by s plus 1. So s minus 1 squared plus 2 squared canceled out. And then for the second part, we have c times s minus 1 squared plus 2 squared. And the s plus 1 and the s plus 1, they cancel out. Okay, so we're not going to simplify this. What we're going to do, just as before, we're going to make some smart choices for s. And the first thing that we can choose is s equals -1, because that makes that equal to 0. So if we look at some smart choices, the first smart choice would be s equals -1. So if we plug that in, we get -1 squared times 2 plus 10 times -1. And then on the right-hand side, we get a, well, actually, we don't have to write that part down, because when we choose s to be -1, this factor becomes 0, and so this whole term disappears. So our first part here is 0. And then we have to add to that c times and then we plug in -1 and then -1 squared plus 4. So on the left, we get 2 minus 10 is -8. And on the right-hand side, we get c times, and this is 2. -2 squared gives us 4 plus 4 is 8. So that gives us 8c. And so we have our first coefficient, therefore, is c equals -1. So another smart choice for s that makes things quite a bit simpler is s equals 1. So if we pick s equals 1, then this factor, or this factor becomes 0, and so everything with a disappears. So when we plug in 1, we get 1 squared plus 10 times 1. On the left-hand side, 2 times 1 squared plus 10 times 1 equals, and now this part disappears, and so we get 0 plus 2b right? That's this term here. And then times 1 plus 1. And then for the c part, we still have the c, and the first part, when you plug in 1 here, that gives you 0. So we have 0 plus 2 squared, or 0 plus 4. Okay, let's evaluate that. On the left, we get 12. And then on the right, we get 2 times 2b. That gives us 4b. And then we have 4 times c. And we just found out that c is -1. So that's 4 times -1. And solving that for b will give us that b equals 4. So b equals 4. Now, we don't really have smart choices anymore. We can just have a convenient choice. So convenient choice, let's pick s equals 0. And when you plug in 0 on the left, we get 2 times 0 squared plus 10 times 0. And then that equals, and now let's plug in 0. So I'll do this a little bit shorter. So 0 for s, that gives me -1. So I have a times -1 and then plus 2 times b. I'm going to write that 2 times b, that is 2 times 4. And then the other part is we have s plus 1, so that is 0 plus 1. And then we have plus c, and c is -1. So that's -1 times, and then that expression here, so that's c times 0 minus 1 squared plus 2 squared. And so that gives us this expression right here. And now simplify all of that. So the left-hand side is 0. This right here becomes -a plus 8. And then -8, -a plus 8. And then times 1. And then plus or minus we have minus 1 times, and this expression is 5. So we have -1 times 5. And when we solve that for a, in the end, we end up with a equals 3. And now we have all the coefficients, so we can plug them into the solution we found here. And so our final solution for the inverse Laplace is 3 times e to the power t cosine of 2t plus 4 times e to the power t times sine 2t. And then the last one was c was -1, so we have minus, and then e to the power -t. And that is our final inverse Laplace.